So in this video, we're going to consider a hash table implementation in C++. Now that we've looked at all the pieces of a hash table, we're ready to do that. Keep in mind there are many ways to implement a hash table, and we're going to start with a somewhat incomplete version, and then in the later videos, we'll improve upon it. Okay, so this class derives from integer set, which was the abstract base class we presented earlier for holding a set of integers. And so I'm going to call this integer set HT with HT at the end to mean hash table. And we're going to override the pure virtual functions that are in the base class. And here I'm showing you a new keyword called override that we can add to functions to tell the compiler that this is an override and it should verify that we really are overriding a function in the base class. Inside here, I also have a constructor that's going to take the size of the table as an argument. I have a integer pointer called table that we'll use to allocate the actual, array that's going to hold our data. The size member variable tells us how big that array is. And then we have a member function called hash, which takes a key as an argument. The data we want to insert is the key, and then produces the index in the table. And then this equation is just something I grabbed online. I multiply the key times 997 and then modulo it by the size. Okay, the override keyword is a special keyword in C++11 that you apply to virtual functions in a derived class. And the compiler just checks them to make sure the virtual function was overridden properly, or otherwise issue a syntax error if it's not. And so this just helps us make sure that we are deriving our classes properly. So I encourage you to use this anywhere you have an overridden function. Okay, so let's take a look at the constructor. When we construct our hash table set, we need to allocate that table array. And so we're gonna set table equal to a new integer array of length size. And again, size is a member variable that gets set to be equal to the argument to this constructor. And then after we allocate that array, we're going to loop over it and just set everything to -1. And so we're going to do something a little hacky here. We're going to set the table entries by default to -1. And -1 is going to mean there's nothing stored there. And what this kind of implies is that we're not allowed to have negative numbers in our set. That's not an ideal scenario. Okay, so this is kind of a bad way to implement things, but just to keep our design simple at the moment, I'm going to use that assumptions. Positive numbers only, 0 or positive numbers, and -1 means there's nothing stored in the array at that position. Okay, so when we do an insertion, what we're going to do is insert a data into our hash table. And so just like we talked about on the slides, the first thing I need to do is calculate the index where that data could be. And so I pass data into the hash table to figure out, into the hash function to figure out where it belongs. That return value becomes the index that I use to look into the table, and I just store the data at that location. Now, this code I've written here is just gonna store the data there without doing any checks. And that's a little problematic because there might already be data stored at that location. Okay, so this code is not good. But what should I do instead, right? What's my alternative? Here are some possibilities, right? If there's data already stored there, it's called a collision. And so what we could do is overwrite the old item. That's what I'm basically doing on the previous slide. That is not a good approach because it loses data, right? When I add things to a set, it should stay in the set. So I can't do this. That code I just wrote, that's bad. What we could do instead is drop the new one and return false. We could fail. We could say, no, we can't take this item. That is also not a good approach, right? We're trying to implement a set abstract data type. It's really not okay for us to fail on such a simple operation. The last alternative is we could try to add it somewhere else into the hash table. Now that's a pretty good approach, but we don't yet know of good ways to do that. So that's what we're gonna do. We're just not gonna do it yet. So it's kind of a placeholder. What I'm going to do instead is the second approach. If the entry in the table is already is empty, then I'll put the data there. But if it's not empty, I'll just fail and return false. This is not a good strategy, but it's a compromise for what we know how to do, and wanting to make progress implementing this code. Okay, now for search, what I need to do, for the search function, I'm gonna get a, actually this should be called find, sorry about that. When I pass in data, I need to calculate its index and then look to see if the data stored at that index is the same as the data I'm looking for. If it matches, then I'm gonna return true, and if it doesn't match, I'm gonna return false. And then for removal, I just look to see, is the entry in the table that's already in the table equal to data? And if it is equal to data, then we update the table at that position equal to 1 to indicate the data is no longer there. That's a removal. Setting it to -1 is equal to a removal. Okay, so all in all, pretty straightforward implementation. There are a few things we need, right? We need the hash table, we need the hash function, and we need to use those two things together smartly. But all this code in each of these functions is really short and just doing a few instructions, a few statements, and there are no loops. And the fact that there are no loops is a very strong proof that this is a fast implementation, that it's O1. Each of these operations is O1. Okay, so the integer set HT class we just wrote provides a basic hash table implementation with all the necessary pieces. It needs some further refinement though for what to do on a collision. And we're gonna take a look at that next.